We're all taught that an amplifier has one specific constant gain, like 100 or maybe 1,000. But, well, that's only part of the story. In the real world, that gain isn't constant at all. So let's dig in and find out what's really going on.
Right, so in a perfect world, an amplifier's gain would just stay flat, no matter how fast the signal is. But in reality, as you crank up the frequency, that gain just starts to vanish. So what's the deal? Where does it go? That's exactly the mystery we're going to unravel in this explainer.
All right, first things first. We have to get our heads around a core principle. An amplifier's performance is totally, critically tied to the frequency of the signal it's trying to amplify.
And this right here is the key. That simple, flat gain we all learn about in school, that's just one piece of a much bigger puzzle. The real world is way more dynamic, and really understanding these changes is what separates a beginner from a pro.
Okay, so to make sense of all this, engineers break down an amplifier's behavior into 3 different zones, or bands, based on frequency, and each one tells a different part of our story.
But before we dive in, we got to define a key term here: bandwidth. Officially, it's the range of frequencies where the gain drops by 3 decibels from its peak. You can basically think of it as the amplifier's sweet spot, the zone where it actually does its job well.
Now this is where it gets really interesting, because this table points fingers at the culprits. See, at low frequencies, the problem is these big external capacitors. But here's the thing, that's really only a problem for older discrete circuits. Modern chips, they don't have this issue. Then you've got the midband. That's our happy place, where gain is constant and everything's perfect. But the real bad guy here, the one that messes with every single amplifier, well, that villain lives up in the high frequency band, and it's the transistor's own internal capacitance.
So we've got our prime suspect, this tiny, so-called parasitic capacitance that's just built into the transistor itself. It's what sets the ultimate speed limit. But the story of why it's such a problem is a little more complex than you might think.
I mean, you'd think, right? A capacitor that's this tiny, we're talking femtofarads, which is just ridiculously small. It shouldn't be a big deal. And honestly, on its own, it really isn't. The problem isn't the component itself.
But here's the crazy part. It turns out the one thing the amplifier is designed to do, to provide gain, is the very thing that turns this tiny little capacitor into a massive speed bump. The amplifier is literally its own worst enemy here. And yeah, there's a name for this whole crazy thing. It's called the Miller effect. It's this phenomenon where that tiny little capacitor connecting the input to the output gets magnified by the amplifier's gain, creating this virtual capacitor at the input that is absolutely massive. This lever analogy is just a brilliant way to picture this. See, you're not just trying to wiggle a tiny capacitor back and forth. You're fighting its amplified twin on the other side. That high gain acts like a giant lever, making that tiny component feel incredibly heavy and sluggish to the input signal trying to move it.
Okay, so let's break it down, because this is the absolute core of it all. You start with a physically tiny capacitor. Then, the amplifier's own gain multiplies its effect, and the result is a huge equivalent capacitor that the input signal has to constantly charge and discharge, which takes a ton of time and just grinds the amplifier to a halt at high speeds.
So, if the Miller effect is our supervillain, who are the heroes? Well, engineers have come up with some really clever circuit designs to fight back. These are the high-speed heroes that neutralize the problem.
Okay, so check this out. On the left, you've got your basic common source amplifier. And yeah, it gets totally hammered by the Miller effect, giving it a really limited bandwidth. But then, on the right, you've got this genius little setup called the cascode amplifier. It basically stacks a second transistor on top, which acts like a shield, breaking that connection that causes the Miller effect. And the result? A dramatic, just huge boost in bandwidth.
And hey, the cascode isn't the only trick up our sleeve. There are other designs, like the common gate amp, that are just built in a way that makes them naturally immune to this whole problem. And then you have source or emitter followers, which are just awesome for their wide bandwidth. That's why you see them used as high-speed buffers all the time.
All right, so all these solutions, all these different designs, they all point to one single, inescapable truth, a fundamental law that governs pretty much every amplifier ever made.
And here it is, folks. This is the big one. This is the rule of the game. In every single design, there is a trade-off between gain and bandwidth. You just can't have it all.
What this really means is that engineering, at its heart, is about making smart compromises. If you need massive gain for, say, a low-frequency sensor, you're going to have to sacrifice speed. If you need lightning-fast speed for a radio signal, you'll have to live with lower gain. It's always
always a balancing act.
So, from now on, whenever you look at a piece of electronics, you can think like the engineer who designed it. Just ask yourself, okay, what was the trade-off here? Did the designers go for power, or did they go for speed? Because now you know the secret. They couldn't have had it all.